Okay, so we are going to solve this problem from the book 1.4, which is a good example on how to normalize the wave function. Okay, so we said that in physics, in quantum mechanics, we are only interested in wave functions that are square integral. That is, in wave functions for which this integral does not explode and is equal to 1. Okay, so this guarantees that the wave function is normalized. We also said that if we check that the wave function is normalized, satisfies this equation at a certain time, then Schrödinger's equation ensures that it will be normalized at any other time. So in this problem, what we have is a wave function at time 0. We want to check whether we want to guarantee, we want to ensure that it is normalized. And if it is normalized at time 0, it will be normalized at any other time. Okay, so they give us the form of this wave function. This big A is a constant, which could be complex. Okay, wave function can be complex. Here is X is the variable. Little a is a real constant. Okay, so we have this shape for the wave function when x is between 0 and a. We could think of x as position, for example. And then it has a different shape. The wave function gets this other shape. This little b that is showing up is another real constant. So, so this shape holds when x is between a and b. Anywhere else, for any other value of x, the wave function is just 0. Okay. So, question A of this problem is normalize this wave function. Okay, so check that it's normalized and be sure that it is normalized. Okay, so what are we going to do? We are going to put this wave function, but always remember the absolute value squared of this wave function. This is the probability density inside this integral, and check what we get. What we want it to be 1. That means it is normalized. All right, so let's write down. Everywhere it's 0 except at this region. So this whole integral from minus infinity to infinity will be shrunk. Now what we only care is the integral between 0 and a. In this part, we have absolute value square of a, x squared over a squared. Okay, so as I said, since this can be complex, I'm using the absolute value. In this case of x and little a, in principle, yes, we also should put absolute value, but as I said, they are real, okay, real numbers. And then after little a, when x is between a and b, we have the other part of the wave function. All right, so this is what we need to solve and ensure that this will give us 1. Well, these are integrals of polynomials, no? So it's not hard to solve. I'm going to get the a square outside. The integral, the little a square is also constant, and then we just have to do this integral, which is going to be x cubed over 3 in that range. Then comes the next one. If you want, you can open this square, and then you would have 3 integrals to solve. But I think easier than that is to do a change of variables and saying that, let's start like this, that b minus x is u, okay? And then this tells us that minus dx is du. So when we do that, what do we have? We put the constants outside the integral. And now this integral goes from a. When x is a, what happens to u? We get here b minus a. When x is b, what happens to u? From this equation, we get 0. Here we have this integral of u squared, and dx, you see here, gives us minus du. So this is the integral that we have to solve. Let me just focus on this integral here. Well, I can get rid of this minus sign if I invert this integral. So I would have from 0 to b minus a u squared du. So this is very simple to solve. It's u cubed over 3 in this range, correct? So let's come back to our solution. We have a squared over little a squared, a cubed divided by 3. Here, a squared, b minus a squared, and now we have b minus a cubed divided by 3. Okay, and you see that now we'll be able to simplify, some, this cubed becomes just a, we get rid of it with a square, same thing here. And so we have absolute value a squared, a over 3 plus b over 3 minus a over 3. So another simplification here. And we got a squared b over 3. We said that this has to be 1. Now the wave function is normalized if this is 1. So what we need to guarantee that it is normalized, we need to have this equal to 1, which means that constant a has to be equal to the square root of 3 over b. This means our wave function is normalized. Very good. This was the story of normalization. Let's go to the next question of this problem, which is just to sketch this function. Okay, so sketch the wave function x0. Okay, so this is my xx. Okay, this is my yx. Let's go back to our definition. Below 0 is otherwise the function is 0. Okay, so when x is anywhere below 0, it's just 0. Then between 0 and a, we have x, okay? And it's a positive slope here. So we have this growing all the way to where? All the way to the point where x is equal to a. When x is equal to a, when x is equal to a here, the only thing that survives is this big A. So this is going to be the maximal value of the wave function. And so here we have that maximal A. What is the maximal A? We found it. Now it's the square root of 3 over b. Okay. Well, now, and this is a straight line, yeah? Okay. Now, above A, we have this part where we have a still linear function, but the slope now is negative. So we'll be decaying all the way to the point where x becomes equal to b. When x becomes equal to b, this is 0. Okay, so then we go all the way to b, and beyond that, 0. Okay, so this is the sketch of the wave function. And this sketch will be helpful for some of the questions that come next. For example, the question C of this problem is, where is the particle most likely to be found at this time 0? No, the sketch here is for time 0. So where is the particle most likely to be found? Most likely is where we have the largest probability, the largest wave function. And this is right here. Okay, so the answer is just x equals to a. The next question of the problem is, what is the probability for finding the particle to the left of a? To the left of a means this area here. This is probability to the left of a. So how do we get to that? This probability to be to the left of a is the integral from minus infinity to a. But we know that in this whole region, the wave function is just 0, so we don't need to put that. We just need to go from 0 to a. And we are talking about probability, so we have to do absolute value square of that wave function dx. So only in the region between 0 and a. And between 0 and a, what do we have? Is this part here. All right, so are we going to put this absolute value squared? So here we have, we get some space, absolute value square of big A, we have x squared, a squared, dx. But this absolute value of a square, we already computed that. We know that this is just 3 over b, correct? We have this a square, which is a constant. From here, we have x cubed divided by 3. Between 0 and a. So if you solve this, you see that these 3 cancel. Here we'll have a cubed, which will cancel with this a square. So the probability is equal to a over b. Okay, so the probability to be to the left in this region here, probability for finding the particle in this region is a over b. The question also asks us about some extreme scenarios. What happens to this probability? Okay. What happens to this probability when b is equal to a? So when b is equal to a, is we don't have this part here. Okay, so when b is equal to a, if I would make that same sketch, we would have a function like this. When x is 0 here, we start growing, reach our maximum, and stop. Okay, so this would be the wave function when b is equal to a. So the whole thing is here. So the probability, just by looking at this plot, the probability has to be 1. And indeed, the probability in this case, when b is equal to a, the probability is 1. Everything is there. Now, what happens when b is equal to 2a? Okay, when b is equal to 2a. Well, then in this case, the sketch, you could check the sketch here is a symmetric sketch, right? Because this region all the way to a, this is a, and then we go to a, yeah? So this region and this region is the same. So the probability here to the left of a should be half of the total probability. And indeed, if you put it b equals to 2a here, you get that the probability is half. Okay, so this is nice. Then the last question, question E of this problem, is the expectation value of x. So how do we compute the expectation value of x? The idea is very similar to what we were discussing when we were talking about, when we were reviewing concepts of statistics. The mean value, expectation value, the average is the quantity with its probability density. That's what we need to solve, okay? And then in principle from minus infinity to infinity, but you know that then you have to break into pieces from 0 to a, putting the correct probability there, and then from a to b. It's just solving integrals of polynomials. You know very well how to do that, so just be careful, and you will arrive at this result, 2a plus b divided by 4. And that's the end of the problem.